Hello, it's me, and I'd like to demonstrate, scramble, and solve Raphael's, what he called the Professor Octaminx. So you saw me do an unboxing on this a little while ago, and I've been meaning to get to this for a while, but I think it's time, now that I have the opportunity, to pull it out and give it a try. So the first thing I do when confronting a puzzle like this is see if I can't categorize it, and from that, maybe I can find a way to work out a strategy for it. So an octamate, really what we're talking about is an octahedron, and it's a corner turning octahedron. So the original version of that would be something like this. This is a corner turning octahedron where you've got these trivial tips, and then you've got this corner turn over here. This is unlike the face turning octahedron, which basically turns on the, well, on the face. This is a corner turning octahedron, and this shares a lot of similarities to the Pyramix. The pieces are very similar to each other. The movement is kind of similar, so a lot of it has to do with taking these wedge pieces and moving them around. And that's really all there is to that. That's all there is to this. So too with this, plus you've got these pieces here which operate as sort of like the central areas here. But it's a lot like this, where you just deal with these wedge pieces. So this is sort of the homologous structure to the Pyramix. Well, just above that, just like you had the master Pyramix, you also have the master face corning octahedron. So there's this guy over here. It just adds another layer to something like this. Let's get this back and get this solved. So this is like the octahedral version of the master Pyramix. The next step up above that would be the Professor Pyramix, and that's this guy over here. So this is a 1, 2, 3, 4. This is a 4 layer. Well, this is 3 layer, this is 2 layers. I don't really count the trivial tips. I'm glad they're there, but I don't really count them. So the Professor Octaminx is the next step up above these guys over here. 1, 2, 3, 4, 5, 6, 7, I guess. 7 total layers over here. This is 1, 2, 3, 4, 5 layers here. But in any case, it shares a lot of similar homologies to it. First off, the cuts of the pieces are similar to it, so these sort of have a tapered look to it, just like this. So it's very similar in that the center pieces here, it's divided into 3. This well, divided into 3 corners in a central center area. So to here, you got a center here, and then you got 3 corners here. So if you're a fan of that, it looks very much like this. You've got 2 central edges here, and then 3 outer wedges over here, and then a tip. So it's just like this, only it's expanded outward. So I'm thinking, okay, if these are all homologies to each other, then maybe I can solve this with similar algorithms that I use with this. So let's see, one of the biggest problems would be how to coordinate the central areas. So I had an algorithm that basically allowed for a very bizarre 5 cycle here, and that's the algorithm itself is very simple. It's just R, and then a deep slice U, RI, UI. Do that 3 times. R, U, RI, UI. That's 2. R, U, RI, UI. That returns you back to the start. What happens is that this piece went here. This actually went here. This green went here. Now this yellow piece went here, and this yellow piece went here. So you had 1, 2, 3, 4, 5 involved in this algorithm. And yet it worked. You were able to work things out because you could rotate this around and put things in a position. So you didn't have to do a lot of deconstruction, just a little bit of rotation. Now might I be able to do something like that over here with this? So let's hold the green one up here, and let's do the same algorithm and see what happens. Will this go to here, this go to here, this go to here, this go to here, and this go to here? Well, let's see. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Okay, so you see this was not touched over here. A white one went here, so that was this. So instead of this one being used, because of the structure of this puzzle, this one participated. So instead of this going to here, this. So it's like if this were here instead. It moves really well, this puzzle. This went to here, this went to here, this went to here, this went to here, and this went to here. So it's the same algorithm, and a very similar thing that happens with this, but it's not this piece that's involved, it's this. So if we're to do it again, we anticipate yellow will be here, white will be here, green will be here, red will be here, and this yellow will be here. This red rather will be here. So 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. Whoops. I went a little further than I should have. Let me keep going until I get it back. I got so excited about turning this puzzle that I just kept going. Okay, anyway, so you get the picture. That's how this is going to work. Just keep going here for a second. It's a pretty fast algorithm, but the very next thing that I'll do is this green will go here, this will go here, this will slide here, this will go here, and this will go here. So 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Now, here's a problem with that though. When doing that algorithm, I have to set things up pretty well. So imagine all these messed up, and I have to set it up to where I have 5 things interacting. That was okay in a Professor Pyraminx because I could move this around to put things in a position. With this, I can't move these around. None of these turn on the face. They're not face-turning octahedrons. So it's going to be difficult to get things set up that if the green is here, it would be easy just to move it to here, but I can't. So ultimately, it would be better if I could find something of a 3-cycle, a way to cycle 3 pieces around. So the next step that I do after looking at this and coordinate and comparing this to other puzzles is I look to see if I can generate other algorithms in order to, well, get a more efficient solve. An algorithm that is easy to remember. No sense in doing a long one that comes out of nowhere. So let's try to do a commutator and see if we can design a middle move. So a commutator is just movements and then undoing the movements. So in this case, we'll call this R, U. We're starting the same way, R-I, U-I. Now we'll stop. Instead of doing it 3 times and getting all those 5, let's look around and see what's isolated here. So we can design a middle move and undo this and only have 3 that are moved. So I'm looking here, all of these are fine, but this is isolated. So because this is isolated, I can move this away and know that nothing else is going to be affected by undoing this algorithm except for this piece. Now I can't do something like this here because if I do R, U, R-I, U-I, there's no similar isolation. There's this that's isolated, but because it's not a octahedron, this will be involved. So I'll just reverse this, U, R, U-I, R-I. So getting it back to here, before I get it back by doing U, R, U, I, R, I, I'm going to take this, do a middle move, and in this spot, pop this over here. Because I know that this, nothing else is going to be affected except this. So now we'll get it back and do U, R, U, I, R, I, and then we simply rotate this back, undo our middle move. So now we have a unique situation with this puzzle that we didn't get with this puzzle, and that's a 3-cycle. This one to here, this one to here, and this one to here. So now I know that if need be, in addition to having that other 5-cycle borrowed from this, I've generated another simple algorithm that really uses the same move, just does it once, provides a middle move in there, then by undoing it, we'll do a 3-cycle. So that's how you find this. Now, again, I always maintain that to solve a puzzle like this, a twisty puzzle, it's not a matter of intelligence, it's a trick. It's like a magic trick. When you learn the trick, then you can solve it and impress your friends. The issue is how to find the trick, how to design your own tricks. But what I'll tell you is even that's not too difficult, because if you understand the concepts of cycling and exchanging and the parity of the puzzle, even that becomes pretty simple. This was just a simple algorithm design, 3-cycle design, based on understanding of what a commutator is. So just to put this into muscle memory, as this goes here, and this goes here, so everything is pointing away. It's all to the right, so it's everything at the rightmost triangle of the center. R, U, R, I, U, I. Bring this in here, then undo it, U, R, U, I, R, I. Bring it back. One more will be the final 3-cycle. R, U, R, I, U, I. Bring it in, U, R, U, I, R, I, and bring it back. Now that wasn't too difficult to design either, and again, solving it is you do it after you understand the trick, looking for the trick, is not too difficult when you understand the movement of the puzzles, and no matter how many layers they are and what shapes they are, if you understand what the commutator is of doing 2 moves and undoing it and doing a middle move, you can design a 3 cycle. So there you have it. Now there's another aspect of the puzzle that might be a little different than the solve of this. Putting these in, I assume, are going to be the same as putting these in. And this is based on the concept of the layered approach. In other words, making things go in by using different layers of putting it in and then doing a different layered move of protecting it. So I think I'll get into that as I solve it. But we have to bear in mind what to do about these centers also, because these centers aren't fixed. These centers do not define the side. And that's because they can be moved around relative to each other. These define the sides because they don't scramble. They turn, but they don't really scramble. In other words, these two don't ever mix with each other. But these centers do mix. I can move them around, I can adjust them. So there's a lot I can do by mixing these centers around without changing the side. So I need to know how to deal with these centers. Now this bears into mind another aspect of how these puzzles are put together, is how to flip areas with each other. So we can either do a 2 cycle or a 3 cycle. We can either do swaps where we have to do 2 swaps at the same time. I can never just, so we're just going to focus on these centers here. Don't worry about all the other pieces. If I were to swap these two, I have to swap something else, like swap these two or swap these two. So if I just decide to do one swap, let's say I go down, down, up, up. Okay, what happened is that these two centers swapped with each other and these two centers swapped with each other. So I basically did 2 swaps at the same time. So that's one way of doing it, where you're always moving 4 pieces. And now that might be kind of cumbersome to move 4 pieces, but that's how that works. Down, down, up, up. So that's one kind of move on these twisty puzzles, is doing swaps, where you have to do 2 at the same time. The other kind of a move is, let's say you don't want to move 4 pieces at the same time, always having the same coordination. Let's say you want to move 3 pieces. So that's what is basically a 3 cycle, and the only difference between a swap and a 3 cycle is the fact that one operates in parallel, the other operates in series. So swapping these two and these two is an example of something that operates in parallel. You're doing 2 things at the same time. But if I were to do 2 swaps but I did it in series, it would be more like a 3 cycle. So in other words, if I were to say swap these two, so this is now here, and then I swap these two, that will turn into a 3 cycle because it is 2 swaps, but you're utilizing one single area to do a swap a second time. So these two will swap, pink will be here, red will be here. Then these two will swap, red will now be here, and purple will be here. So if red is here and purple's here, it's like this one to here, this one to here, and this one to here. So in that way, 2 swaps can turn into just 3 pieces that are utilized. So let's see if we can do something like that. How do we do something like that? Well, let's start off again with our down, down, up, up. And then what we'll do is we see that we have a middle move here, so to speak. This is isolated. So I'm going to move this up like so. And then I'm going to finish it by doing down, down, up, up, and move this back down like thus. Okay? So what happened there, it was a pretty clean exchange. This went to here, this went to here, and this went to here. So that designed a 3 cycle much like these did. But understand what I did is it's the same concept of swaps. I basically swapped these two, and then I swapped these two. That was done in parallel, in series rather. So if you do swapping in parallel, you swap 4 pieces, basically 2 pieces and then another 2 pieces, so 4 pieces are involved, 2 exchanged and then 2 others exchanged. If you do the swapping in series, then you end up with a 3 cycle, because this will always be involved in the swap. First this one and then this one. So these two and then these two. So if we do that again, down, down, up, up. Let's move this up, and then down. You're just basically doing the opposite. Down, down, up, up, and then we move this back down. So one more 3 cycle should do it. So again, a 3 cycle is simply swapping, doing 2 swaps, but doing it in series so that you can make it look like 3 pieces. So once again, down. Now this bears something else in mind too. I have a choice. Maybe I should reduce these centers first and then get these guys in, because now I can move these independently. So down, down, up, up. This goes up, and down, down, up, up, and this goes down. I think I was supposed to go down, down, up, up. Okay. So those who saw that probably yelled at the screen saying, "Stop! You're going to make a horrible mistake." Anyway, so the purpose of that is just to see if I can design 3 cycles here and design 3 cycles here. Once I've done that, I think I've got it. I think I have a way to classically solve this puzzle by doing 3 cycles to move pieces around. Again, it starts off with correlating it with other kinds of puzzles that you've done. And if you don't have other kinds of puzzles, you look to see what kind of swapping can you do. Are you going to do it in parallel? Are you going to swap 2 pieces and then 2 other pieces, so 4 pieces will be involved? Or are you going to do it in series, where it's going to be a 3 cycle where your 2 swaps involve one that is the same piece? These 2 and then these 2. So coming up with a commutator is not difficult. You saw that it was quite easy. The other issue is strategy. So when I have a more complex version of another puzzle, you can see this sticker came off, I don't know where it is, and this one got smudged somehow. It was somebody's name. But anyway, what overall strategy? So there's a microscopic strategy of moving specific pieces around. Then there's a macroscopic strategy of the general approach to this puzzle. Am I going to put piece in after piece in? Am I going to solve the centers first? Am I going to reduce it to a more simple puzzle? So what's a more simple puzzle version of this? Am I going to take both of these, reduce it to this, and solve it just like this, or I'm just solving these wedges? Maybe what I should do is take this and reduce it to one of these guys and then solve it as such, where when I do that, it'll look like this. These corners will be here and the center will be here. So I could do that. So here's another concept related to puzzle solving. When you have a face-turning puzzle, it's best to reduce it to a simpler version. A 4 layer reduced to a 3 layer and solved as such. Corner turning puzzles, I don't really recommend solving it like that. And the reason just has to do with the structure of the puzzle. So, for instance, here is an example of the face-turning, master face-turning octahedron. This one I do solve by reduction. I reduce these guys and these guys, and I basically solve it. As such. But this I don't. What I do is I put it in piece by piece. Corner turners, because they don't have an actual face. They have a face, but it doesn't turn at those faces. It becomes difficult to reduce it and then solve it as such. It's actually easier just putting the pieces in one by one. Here's the, I guess the elite version of the face-turning octahedron, made by Raphael as well, another great puzzle. And this I also do the same way, as I reduce these edges, and then I reduce the centers, and it's a lot more consistent to move it on the face and then to solve it as just a face-turning octahedron. Also, a corner turner, you do it piece by piece. Okay, so now that we've looked at it, we've looked at the microscopic strategy of placing these pieces in, the macroscopic strategy where we're just going to do each piece individually, but with various algorithms. And now that we've designed the algorithms, which are the trick based on our concepts of what commutators are, now that we know the trick, let's go ahead and do it. So I'm first going to turn these. Now you may think, why even design it with this? Because it's trivial. And the answer is because I like the way it looks. I like there to be trivial tips because it keeps the integrity of the shape. And when you're doing a twisty puzzle, the shape has everything to do with the presentation. So we're just going to go ahead and turn this. Now, Raphael does sell these puzzles, and I recognize that a lot of people look at this video to see, should I buy this? And of course the answer is always yes, you should. You really, really should. To challenge yourself and to enjoy a masterfully made puzzle. So far there isn't any puzzles that he's ever made that he's not put out there and put his name to that hasn't been well worth it. See, I'm always tempted to move this. I have to keep bearing in mind that this is a corner turner. So you can see the movement is highly satisfying at each level. The more superficial levels are the easiest to turn. You've got 2 superficial levels. The deeper levels are a little bit more sticky, but nothing too bad. So go here, 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 here. Okay, so we're going to keep going until we're sure that I've spared no expense with a challenge. Oh. Nope, it's not a face turner, it's a corner turner. And turn, turn. Okay, it looks like that's pretty good. These guys are still... Okay, so that's pretty good. There it is, a scrambled Professor Octaminx in all of its scrambled glory. Now what's fun about these puzzles is when you take a look at, say, a scrambled Rubik's Cube, you feel compelled to try because it doesn't look impossible. It looks like it could be difficult, but 4 sides, not too many pieces on each side, you're wondering how many sides you could do. When you see a scrambled puzzle by Raphael, an over-the-top kind of puzzle, and that's what a puzzle beyond, really, I guess a 6x6, beyond a 6 layer, would be something like an over-the-top, you wonder how it is actually possible. It's one thing with a Rubik's Cube, with a 3x3, to solve all the layers, but when you look at something like this, it seems almost impossible to think that you're supposed to put all these colors in the right place and they're supposed to be the same color. So the key with this is, of course, learning the trick. So let's see how far we're able to go with this, as it looks very impressive in a scrambled state.